We'll try one more of these. Practice number 6. A popular magazine reported that 5% of American adults are afraid of being alone in a house at night. Say a random sample selects 20 American adults. I like this one. Find the probability that at least 3 people in the sample are indeed afraid of being alone at night. And we'll round to 3 decimal places. Okay, so we can apply the binomial distribution here. So I just had to pause while a garbage truck drove by my house. Why does this fit the binomial? Right? Okay, well, there are a fixed number of trials. How many trials are there? In this case, there are 20. A random sample selects 20 American adults. So think like each one of those is a trial. We're going to ask them, are you afraid of being alone in a house? Right? They're all independent, so the answer to one doesn't influence the answer to anyone else. And there's success and failure. What is a success? What would we consider a success in this case? And a success would be that if the person did indeed respond that yes, they're afraid of being alone in a house at night. And a failure would be if they say, no, that's not a big deal to me. Okay, also, we notice the language in the question. It says find the probability that at least 3 people in the sample. Okay, and you see those words at least, and think, what does that tip you off to do here? Okay, so let's go ahead and attack this problem. So find the probability that at least 3 people. So there's 2 ways to go about it. There's a very, very difficult way, a long way, and then a way that is still, I'll just show you all this, a way that is still going to be a fair amount of work, but not nearly as much as the other one. Okay, so hopefully you said, when I asked, hey, at least, you said, oh, that means use the complement. All right, so let's compare the 2 ways we could do this. The first is without the complement, and the second is with the complement. So when they say, find the probability that at least 3 people in this sample of 20, you could write it as the probability that x is greater than or equal to 3. At least 3 or more. So if we did that, then you notice that the formula to calculate probabilities with the binomial distribution, they're always for exactly a number, right? We don't have a formula for at least 3, but we can calculate exactly 3, or exactly 4, or exactly 5, or exactly 20. So if we wanted to calculate this, it would be a lot of work. If we did it directly, if you will, we'd have to find the probability that exactly 3 people are afraid, plus the probability that exactly 4 people are afraid, plus the probability that exactly 5 people are afraid, and we'd have to keep calculating these until we got all the way up to the probability of exactly 20. And each one of these calculations would need that big formula every time. Okay, so it's possible to do that, but we can save ourselves a lot of work if we realize, ooh, it says at least. Maybe I can take advantage of the complement. So here we go. The probability that x is greater than or equal to 3 is equal to 1 minus, and then think, okay, what is the complement? Another loud truck driving by. Okay, what is the complement of greater than or equal to 3? And it's less than 3, right? Kind of think of like a number line. So greater than or equal to 3, less than 3. It goes the other direction, right? It's all the other numbers. So this is the way we're going to go about it. And then we'll do the 1 minus to finish it off. Okay. Now as I continue, I've just copied this part down here. 1 minus. What do we actually need to calculate then? If x is less than 3, then that means we're going to find the probability of 0 plus the probability of 1 plus the probability of 2. So it's not going to be just one calculation. There's still going to be a little bit of work here, but we have to calculate 3 versus calculating, like 18 of them the other doing it the other way. Okay, and each one of these is going to require that big formula every time. Okay, so I'll just kind of keep that there. Let's start with the probability of 0. Actually, I think we need to go back and name all of our values to plug into the formula. Let's do that. What is n? Okay, as we said it a moment ago, but here, how many trials are there? Well, there are 20 people in the sample, so there are 20 trials because like we ask each one of them. What's the probability of success? So we're going to define success as the person saying that they are afraid, and there's only a 5% chance of that, right? This magazine reported 5% of American adults are indeed afraid, so just a 5% chance of that happening. So what does that make for the probability of failure? And it's got to be 0.95 because they have to together add up to 1. And the truth is there's really a complement going on right there, right? P and Q, they have to add up to 1. So 0.05, the other's got to be 0.95. And okay, so as far as x goes, the x changes for each one of these. We'll begin with x equals 0, then x equals 1, x equals 2, calculate each one. Okay, let's go for it. The probability of 0. So, well, you see it right there, but let's talk through it. All right, it's n factorial, so we've got 20 factorial over x factorial. Well, we're taking x to be 0. X is always right here, by the way. So x is 0, 0 factorial. And then the next one is n minus x. Well, 20 minus 0 is 20. And another kind of what we said before, another good way to remember this, these numbers are always going to add up to that number. So if this is 0, then, well, that's got to be 20. Okay. And then the probability of success, 0.05 raised to the x, the 0, times the probability of failure, 0.95 raised to n minus x, well, and there's the 20. Okay. So hopefully you're comfortable with that. What we'd like to do now is simplify these factorials. And we notice right away the 20 factorials just cancel out. Now, something interesting here, the entire numerator canceled. Hey, if the entire numerator cancels, remember, then it becomes a 1. Also, down here we have 0 factorial, and if you remember, 0 factorial just equals 1 by definition. So this fraction out in front is 1 over 1. Or you might just think of it as being 1. And then we have times 0.05 to the 0 times 0.95 to the 20. Now, if you want, you could grab your calculator right here and put these numbers in and get your answer. For others, maybe you realize, oh, 1 over 1 is 1. We really don't even have to write this here because, we're multiplying a 1. Also, maybe some of you guys remember raising to the 0 power. It works in a very similar way as 0 factorial. 0 factorial is 1, and any number raised to the 0 power is 1. So this whole thing is just 1. Turns out all you would have to put into a calculator is 0.95 to the 20. And when you do that, rounding to 3 decimal places, this is what I got, 0.358. Now, if you didn't remember that raising to the 0 power is 1, no big deal. Put this into your calculator will do that for you. You don't have to know that. But it does, if you do, why not? It makes your typing in a little bit simpler. Okay, so we just found the probability that nobody from these 20 says they're afraid, right? Probability of 0. The chances that nobody out of this group is afraid of being alone in a house at night. You know what I should have mentioned earlier, even back here? It's easy to forget the 0, right? So less than 3, remember we're only talking about whole numbers here, discrete random variables. So, people remember the 1 and the 2, but they oftentimes forget that, maybe the result is 0 successes. So 0 successes, 1 success, 2 success. Don't forget in a case like this that, there might be 0 successes. And that's what we have. It's actually a pretty good chance of it, 0.358 chances that nobody ends up being afraid. Okay, moving on. We need to find the probability of 1 success. Okay, so it starts off the same way, 20 factorial over 1 factorial. And then, well, if 1 factorial is here, what goes here? Got to be 19 factorial. And then 0.05 to the first and 0.95 to the 19. Okay, let's simplify what we see here. And now, hey, here's one of these cases we saw when we were reviewing factorials, 20 factorial over 19 factorial. So we could think of that as 20 times 19 factorial over 19 factorial. These would cancel, and we just get 20. And it's divided by 1 factorial. Well, that's just 1, so that's not influencing anything. We've got 20, and then 0.05 to the first, 0.95 to the 19. Grab your calculator. And here's what I got, 0.377. So chances just slightly better than 0 people saying they're afraid. The chances of 1 person being afraid out of that 20, 0.377. Well, we've got one more calculation to do. We need to find the chances that exactly 2 people out of our survey, out of our sample, are afraid. We're going to say, okay, the probability of 2, 20 factorial over 2 factorial times 18 factorial, 0.05 to the 2, 0.95 to the 18. Now what's going on here? 20 factorial over 18 factorial. Think of it as 20 times 19 times 18 factorial over 18 factorial. Those would cancel. What's 20 times 19? 380. Okay. Oh, well, it looks like I just left it. So, yep, those cancel. 20 times 19 over 2. And I just copied the rest, and then, okay, that's 380 divided by 2. So we end up with 190 out in front when we simplified all that, times 0.05 squared times 0.95 to the 18. Grab your calculator at this point, and you should get 0.189. That is the probability that exactly 2 people from our group are afraid. Okay, now we can wrap things up. Going back to our strategy from the very beginning, this is what we were trying to find all along. At least 3 people, x greater than or equal to 3. So we said, okay, we're going to find the probability of 0 plus the probability of 1 plus the probability of 2, add all those up, and do a complement. And I just went straight to the final answer here. 0.076 is the chances that at least 3 people are afraid. Now that's surprising. That's very low, right? I mean, it's 7.6%. Well, because the probability of success is very low. Only 5% chance that any one of these people, or that each individual, right? So if you're talking to get 3 people, even 3 people or more, the chances are not very good. Okay, let's stop here.